Good morning, everyone, or at least what will be morning once you receive this series of lectures. Dr. Goodwin, uh, I will say that I've missed you, even though I'm the only one that has the camera on. I have missed our virtual presence with one another. It's been an interesting 7 weeks, but let's get into the outline of what we're going to cover today. And again, our calendar has zipped by really fast. This was the original YouTube lecture I promised. Our last lecture, which I hope you'll join me for, will be November the 18th, next Saturday. This is someone that I thought you ought to know about. Dr. Gladys West, born October 27, 1930, in Sutherland, Virginia, American mathematician, known for her work for contributing to the development of the Global Positioning System, or GPS. Gladys May Brown was born in rural Virginia, where her parents owned a small farm in an area populated mostly by sharecroppers. Growing up, when not in school, she spent much of her time helping to harvest crops on the family farm, an occupation she knew many of her peers would continue into adulthood. In her community, the only clear options for a young Black girl's future were continuing to farm or working at a tobacco processing plant. But at school, her talent for learning offered another path. As valedictorian of her high school graduating class, Gladys received a full scholarship to Virginia State College, now Virginia State University, the historically Black college, where she earned a degree in mathematics in 1952. She later returned for a master's degree in the subject, graduating in 1955, after spending time teaching math in racially segregated Virginia schools, and after applying for a series of jobs in Virginia's segregated state government that were instead awarded to white men. In 1956, Gladys was hired as a mathematician by the U.S. Naval Proving Ground, a weapons laboratory in Dahlgren, Virginia. I hope I'm pronouncing that right. As the only fourth Black employee. There she met Ira V. West, another Black mathematician on the base. The couple married in 1957 and have 3 children. At Dahlgren, Gladys West was admired for her ability to solve complex mathematical equations by hand. She eventually transitioned from solving those equations herself to programming computers to do it for her. One of her major projects was work on the Naval Ordnance Research Calculator, an award-winning program designed via 100 hours of computer calculations, which often had to be double-checked for errors by hand to determine the movements of Pluto in relation to Neptune. In 1978, West was named project manager of CSAT, an experimental U.S. ocean surveillance satellite designed to provide data on a wide array of oceanographic conditions and features, including wave height, water temperature, currents, winds, icebergs, and coastal characteristics. It was the first project to demonstrate that satellites could be used to observe useful oceanographic data. One of West's work on CSAT came GeoSat, a satellite program to create computer models of Earth's surface. By teaching a computer to account for gravity, tides, and other forces that act on Earth's surface, West and her team created a program that could precisely calculate the orbits of satellites. These calculations made it possible to determine a model for the exact shape of the Earth called a GeoID. It is this model and later updates that allows the GPS system to make accurate calculations of any place on Earth. This is what we're going to cover today. And as I said, I'm going to cover this in a series of YouTube lectures. So there's going to be 6 parts. The first 5 will pretty much cover linear equations. The last one will be word problems because you just can't get away from word problems. So I'm going to stop sharing my desktop. Pause the recording, and then I'll turn it back on and change to the document camera, and we'll get into the first lecture. So this is the first of 6 parts. So what I'm going to do is I'm going to do a little lecture, and then I'm going to show you the homework. And then from that, with just the YouTube link and the homework that I'm going to send you, you should be able to do the homework fairly easily. And a lot of the sections are not that hard and not that long. But again, short lecture number 1. One of the types of questions you will see on the SAT is solving systems of linear equations, sometimes called simultaneous equations or 2 equations with 2 unknowns. A system of equations can be solved in 3 ways: by substitution, by elimination, and by using the answer choices when answer choices are given. When the alternative of using the answer choices is used, we substitute an answer choice in each of the 2 equations and determine which one works. The correct answer choice must work in both equations. Let's consider the following example. Here we have a system of 2 equations and 2 unknowns. 3x plus 4y is equal to negative 23. Negative x plus 2y is equal to negative 19. Which ordered pair in the given 4 options satisfies the system of equations above? So in other words, what works for one has to work for the other. So in the first one, if I put an ordered pair there, that one side, both sides has to equal negative 23. And if I use the same ordered pair, then that same ordered pair has to equal negative 19. Let's start with A. Well, the first ordered pair checks out. Let's see if it works in the second equation. That's the x. Negative times a negative is a positive 5. Positive times a negative is a negative 4. And 5 minus 4 is 1. And that does not equal. So that does not check out. Now let's try 3 and negative 8. So we're going to try B. Positive 4 times negative 8 is going to be negative 32. And negative 32 plus a positive 9 is going to be negative 23. So this one checks out. Now we're going to try the second equation. 2 times -8 is -16. So that checks out. So your answer is 3 and -8 because they both work in both equations. Now let's go to your homework. So this again relates to the lecture. Given the following, x plus y is equal to 0, 3x minus 2y is equal to 10, which of the following ordered pairs satisfies the system of equations above? Second question, given x plus 2y is equal to 7, 2x plus 3y is equal to 11. Same question, which of the ordered pairs? So in each one of these cases, and in the last one, of course, minus 2x is equal to 4y plus 6, and then 2 times parentheses 2y plus 3 is equal to 3x plus 5. Which of the following ordered pairs satisfies the system of equations above? So if you notice, it's a little bit different in the fact that the first two look like what we just went through. And then this one, we're expecting you to get it into that system of equations that we talked about, and then try doing the substitution. So I think you have everything that you need to be successful.